So the Baylis-Hillman reaction is one of our new orgo-named reactions, and it involves the coupling of an aldehyde with an activated alkene, so our double bond with an electron withdrawing group attached. The reagents we would use for this would be a tertiary amine. So NR3 is our general tertiary amine. A couple of examples, one that's come up in the literature is DABCO, which is this structure. And for a orgo-1, orgo-2 equivalent that we would have seen before, ET3N or triethylamine, which is this structure, is something that we could put in as our underlevel equivalent for something we've seen before. So when you take your aldehyde and activated alkene and treat it with your tertiary amine, you get this product in a Baylis-Hillman reaction, which takes this, used to be our aldehyde, and as this kind of looks like it used to be our alkene. So they come together, you keep the double bond, you don't lose it, and your aldehyde turns into an alcohol. So that's the general overview of the Baylis-Hillman reaction. Let's take a deeper look at the mechanism, and then we'll come back and do a predict the product example, and we'll look at a literature example.
So the Baylis-Hillman mechanism is pretty simple. We take, this is our aldehyde, and this is our ester. And the first thing is to start over here with our ester and the tertiary amine, which attacks the double bond, swings that up and up onto the oxygen, giving us a positive on the amine and a negative for our enolate intermediate. We then take the enolate, swing it down, attack the aldehyde, swing that up onto the aldehyde oxygen, which gives us this, where the amine is still positive, and now this oxygen has the negative. So we're going to use HB as a general base as our proton donor to protonate this oxygen to move forward, which gives us the next product. And then we're going to use general base, which would be our tertiary amine, but we're just going to use B- for this illustration to eliminate this hydrogen, swinging that up and onto the oxygen, which gives us our enolate here. And then we're going to do our E1CB elimination to get our tertiary amine back off. Swing down, which kicks that onto the positive amine. Forgot it over here, my bad. Swings that up, and we get our final product, which has the alcohol where the aldehyde used to be, and our double bond still there. So that's the mechanism. Let's look at it, predict the product problem.
So now that we've taken a look at the mechanism and we understand a little bit more about the reaction, let's try this predict the product example. I've left the general reaction up here, so now we're replacing just the general R group with an arrow group on our aldehyde, and our alkene has become this. So now we have an R group on both sides. So we're treating with DABCO, our tertiary amine. So you can pause the video right here and try to figure it out for yourself. Otherwise, we're going to go right into the answer. So remembering our mechanism, we know that this is going to be attacked by our NR3, and we're going to get something attaching here. So this is going to swing up, and that's going to swing up to give a negative on the oxygen when we come back down. So if we swing up there, we're going to attack that. So we keep our ring. We keep our electron withdrawing group. So now the key thing I said at the beginning is we don't lose this double bond. So that stays there. So now the only question is which end of the double bond did the aldehyde add to? So looking back at our mechanism, we know it added there, and it became an alcohol. So now I'm not drawing this as a certain enantiomer, kind of like I did up here, because depending on your base, you will get a different one. That's the product. Let's take a look at a literature example now. So here we have a couple literature examples of the Baylis-Hillman reaction from within the past 5 years, 2013 and 2017 respectively. So the first one is pretty similar to the basic example we've gone through in this video, where we have the arrow group with an aldehyde, our ester with double bond, DABCO is our general literature tertiary amine, and we get this expected product. A little bit more interesting of a literature example is this second one, which we have our activated alkene, but it's 2 double bonds in a row. with our normal aldehyde. MTBD is just another hindered tertiary amine. And we get this product where it adds to the end of the second. And if we were to go through the mechanism for that one, we'd still get the tertiary amine attacking here, but this would swing up to there, and then go up into our electron withdrawing group like normal. And then when it attacks the aldehyde, it would just swing all the way down through. And that's how we get the substitution down there. So these are just a couple examples from literature where this one was used to further synthesize a bunch of things, since we have an alcohol, a double bond, and an ester that we can all do chemistry with. This one was in a paper that was more proof of concept, just to show that yes, it does add there instead of here or here. Hopefully you enjoyed this video on the Baylis-Hillman reaction. It's pretty interesting, pretty simple, and used in a lot of organic syntheses for more complex molecules where you just need to get a couple things connected together right away.